Yeah, it's no worries. Sorry if you're listening at home, I forgot to record that, so there's your notes. All right, now the question is, wow, this work. All right, here we go. Parametric equations part 2. We've done the derivative. Now let's, I think in order for this to go well, I'm going to switch the order just a little bit. I'm sorry to play around with you, but you're usually the byproduct of me tweaking and improving the lesson. I feel like if I would have done the last part first, it would have gone better. So would you go to the part where it says objective, find the slope of a tangent to a parametric curve? You see where I'm at? I think it might be on the back. Okay. Let's build off the first derivative we know before we go to the second derivative, which is really the biggest part of the lesson. This will come more and more as we go on this semester, but you're going to do one huge type of parametric equations that is used in real life, especially physics, is for projectile motion. If, for example, you shot a cannon at a pi/4 angle at 30 meters per second, which is not actually very powerful, then the projectile motion would follow that kind of path. Gravity eventually takes hold. Yay? Now I could describe the position of this not with y and x equations, like where it is horizontally relates to where it is vertically and vice versa, they relate to each other, but instead talking about where it is horizontally depends on time and where it is vertically depends on time, and writing this path in projectile, or sorry, parametric way. Now start by looking at the cosine, or the x component to this here. The only thing that contributes to the horizontal position is the original firing of the cannon. Gravity doesn't affect horizontal position. And as far as original position, that doesn't really affect it either, because we usually just define where it's fired from as the starting point, all right? So this is strictly, it's only the the horizontal component to the firing times time. Think of it like this. If this original firing was 30 meters per second at a pi/4 direction, then this original component to the velocity is the adjacent part of that. And so it would make sense to say that the cosine of pi/4 equals that adjacent part to the vector over the hypotenuse. And so that velocity component horizontally is 30 cosine pi/4. And that's meters per second. If I wanted the x then, it depends on the horizontal component, or change in position, times time, or the velocity we just found times time, and that's where they're coming with 30 cosine of pi/4 times time. How far it goes horizontally in meters per second, or how fast it goes horizontally in meters per second, times some number of seconds. The y depends on three things. What's the negative 4.9 t squared part? That's with respect to gravity. That's where gravity affects. Integrated. That's the vertical component to the firing, to the projectile, how much we contributed to its position. And what's the 2? Do you reckon? What? Yeah, the initial. And it started at time 0. The 2 terms in the front would drop away, and y would be 2. Now, the hard part is the second question. That's where the real calculus thinking comes in. So you've got this projectile, and it's firing a cannon, whoosh, and they want to know what's the angle at the instant it hits the ground. Now that's important, because at the instant, this angle and this angle and this angle and this angle, they're constantly changing. So I want to not talk about some really big triangle. I want to talk about the most microscopic triangle I can. At the very instant, at the last second, right as it's hitting the ground. Well, if it's microscopic, then what's this thing? dy. And what's this? dx. And this here, that's the question. Now this is key for a lot of things. I mean, if you're a basketball player, it doesn't take any genius to know that you can't hit a basket shooting a really flat arc because it'll clang off the rim. It has to be a sufficient arc so that it clears the front of the rim and drops through the hole. So there is definitely a range of possible angles that'll actually hit from. So in this case, the angle is the matter. What matters when it hits? What's the angle? So get me started. What do you think? How could you find theta? Come on, I could get a trig kid to come in here and do that. Inverse tangent of dy over dx. Now, given that we have parametric equations, not x and yx equation, then that really, we typically do that by dy dt over dx dt. And let's talk about when. When matters. When do we want the derivative? We don't just want the derivative at any old point. We want when it hits the ground, okay? All right, so it feels like to me we have 4 components to this. We really first and foremost need to know when it hits the ground. I can't find dy dt or dx dt at the instant unless I know the instant. So let's find when it hits the ground. When it hits the ground, what do you know? X or y? Y. Y is 0. So you take this equation, which is quadratic, this big gross mess, what is it, 30 cosine, sine, rather, pi over 4t plus 2, and you'd solve. What kind of solutions would you expect? Real or not real? You should have real. One positive, one negative. The negative one, what does it indicate? Yeah, if you kind of went back in time through the cannon to when it hit the ground before the cannon, that's the negative time means nothing. It has no meaning, right? It's the positive. You choose the positive time. Now, if we had all the time in the world, we will do this later, and we'd store that. Okay? Then we would take the inverse tangent of, now what is dy dt? Negative 9.8t, and what's the other part? 30. What's sine of 30? Or sine of pi over 4? Root 2 over 2, and t goes away, yeah? All right, over, what's dx dt? Root 2 over 2. Wait, at this time stored, or when it's hit the ground. Now, I would imagine that you're going to get a negative angle because I think this would probably be y is decreasing, yeah? You'd probably choose the positive angle or make the angle positive. You just wouldn't say to your artillery commander, well, it's going to hit at a negative 3.2 radian angle. You'd say the angle is going to be below 5 degrees, right? Right. Now, let's go to parametric part dos. I'm going to, I feel like some of these notes fell flat on their face. It all made sense to me when I was writing them, but when I was teaching it, it's different. Sometimes there's some problems I just think of in a way that doesn't teach well, and this is one. So I'm going to change this as I go to a little more traditional. This I like, all right? The second derivative of parametric is largely a notation issue. There's one little gotcha in there that people don't understand why they're doing. It feels like you just, if the first derivative is dy dt, if we typically do dy dx is y prime over x prime, then if I do the second derivative, why not y double over x double and call it good? Well, that is actually not true. There's a bit of a chain rule thing in here that makes it a little more complicated than that. And I'd like you to actually understand why you do what you do and not just memorize something that doesn't make sense, all right? So let's go to notation. When you took the derivative with respect to time, way back when calculus was new, and you were just starting to get a feel for all the crazy notations that come with calculus, and you would say stupid stuff like, so you multiply by d over dt, and your teacher would say, no, you don't multiply by d over dt any more than when you solve this, you don't multiply by the square root symbol. That's stupid. You don't multiply by a freaking symbol. It's an operation. That's ridiculous, all right? So I think we all know, and if you don't know, then please fake it, that you're not multiplying by d over dt. It's not a thing to be multiplied by. It's an operation. You're taking the derivative of both sides with respect to time. Yay? When you did that, you typically wrote it this way. dv dt is, on this side, you take the derivative. It's now, you had to learn the chain rule first. You do have this outside derivative. It's 4 pi r squared, but you do have a derivative of the inside. The derivative of the inside r with respect to t is dt. All right, now, you guys are so far past that this notation stuff is all making sense. Let's just now, think about this then. When I say differentiate this with respect to x twice using Leibniz notation, then I'm going to take y and differentiate with respect to x once, and then I'm going to take the derivative of that with respect to x. So I'm going to take the derivative with respect to x and then take the derivative of that with respect to x. That's what a second derivative is. Okay? That's why in notation of the second derivative, it's actually the derivative of the derivative of y, which is y the 2 goes there. And the derivative with respect to x twice, which is y that 2 goes there. Try explaining that to a California kid who's just learning it, it means nothing. Okay? What about the other side? Well, it's the derivative with respect to x, and the derivative of respect to with respect to x of x to the 4th. The first derivative is 4x cubed, and therefore the second derivative, when I take the derivative of that, is 12x squared, and because it's with respect to x, there's no dx. You with me? Okay, good. I'm assuming you're great. Let's talk about now then this. Would you, these I felt like made sense last year and it flowed well because I had just written them last year, but now I feel like it was choppy. So just stick with me, all right? This is the question, and we're going to go through this really solid calculus stuff. Let's start by finding the first derivative. We know that dy dx is dy dt over dx dt. Yeah? dy dt is 4t cubed, and dx dt is 2t. Let's also clean it up and say dy dx is 2t squared. Go? All right. Here's the second part. Take the derivative of that, but the question is, what with respect to? Well, if I want the second derivative of the curve, then it needs to be with respect to x. If I take the derivative with respect to x of the left side, then I have to take the derivative with respect to x of the right side. And because I'm taking the derivative with respect to x, I'm going to have a chain rule component to that right side in a second. The left side is the second derivative, Leibniz notation. But on the right side, using chain rule, what's the derivative of the outside? 4t, and the derivative of the inside? dt dx. Now that's kooky, okay? It's much more typical. You move the dt dx to the denominator. That is to say, this is the same as 4t over dx dt. The reason being that you'll usually have dx dt in your work somewhere. You don't want to go back and differentiate dt dx. You want dx dt because that's what you're going to be working with typically. All right, then you sub in dx dt. What is dx dt? 2t. So your second derivative is 2. Okay. Now if we were to go back and check that by a little bit of, eliminating the parameter, we could get a yx equation, take the second derivative and see that, but that's what you would see. You follow? All right. Let's then, so in essence then, what you're seeing here is really the derivative of the derivative over dx dt. The second derivative, you might write that as a note. Second derivative is the derivative of the derivative divided by dx dt. And the dx dt is a chain rule outcome. Okay. All right. Let's try another. Or actually, yeah, we'll do one together and then you'll try one more. Okay? So, second derivative of this equation. What should I do first? Find dy dx, which is dy dt over dx dt. Don't go beyond our good basics. You should still, when finding dy dx, communicate to the reader how you find it, and that's dy dt over dx dt. That should still be done. dy dt is 3, dx dt is e to the t. Do you want to leave it like that or rewrite it 3e to the negative t? Negative? Or leave it, did you say? If I leave it like that, then I'm going to have to use the quotient rule in the next derivative, yeah? So I'm feeling like rewrite is probably the better way, so I don't have to use the quotient rule next time around. So the second derivative would be to take the derivative with respect to what again? X of 3e to the negative t. The derivative of the outside is negative 3e to the negative t, but I pick up a dt dx, yeah? Now you can, definitely as you do more and more of these, blow off that chain rule and start saying, when you do the second derivative, it's just the derivative of the derivative, which is negative 3 to the negative t, divided by dx dt. And what is dx dt again? E to the t. What are two other possible ways to write that cleaned up? Negative 3 over e to the 0 or over e to the 2t? 2t or negative 3 e to the negative 2t, either one of those. You follow? All right. Try the next one on your own then, please. up to cotangent, or did you leave it cosine over sine? What the heck? Where did the time go? Oh, sorry. So this homework is due Friday. The test review key will be online, and I'll be here tomorrow after, before school if you have questions. Make sure I get 118 today. You don't want to get behind, right? Yeah. Oh, if you have the areas blank, that's okay. I'll get to it. Am I right? Right. Have a good day. That's that sound of silence there, that's the oh crap sound. I did get the fingerprint on this. I gave them a little bit. The only thing that can really get them off people didn't I feel like when I was saying, like, well, I didn't so I took off a whole thing to get into space after that. So here I was just closing. That's what I was at. You go 13? I did it. One, yeah.
Oh yeah, I know one. And then right, since it's 1 9.
I think I had work, so that's so this is I think that's 17. We're up here. Hi. Yes, I have it. I just haven't been it. I'll get it done there.
Do you have any pre-kids who lost the book?
No, but I have a couple kids that just.
Oh,
Oh, really?
Yeah.
Oh, no. Okay. My kids should have all their names in the front cover.
You know how I also switched the last
Well, actually, you know what? Yes.
Yeah, that was like 103. Yeah, just like
Yeah.
Might be on the ground.
Mr.
Yeah.
Can I go to the stats meeting, AP stats meeting?
Is that today?
Yeah, it was moved from like 2 weeks ago.
Oh.
I think
Okay, so you're sitting up here and you're over there conducting stuff?
probably. I don't know.
It'll just take a couple minutes. Hi.
Do you mind if I go up to Claypool and talk to my scholarships from this class?
Oh, so you're signed up here.
I tried to do a pass, but I kind of don't want to bother with class.
Is it gonna take the whole period?
I highly doubt it.
So you're gonna come back here when you're done?
Yeah.
I need to like like look up where to buy chocolate stuff. I don't know where we can do this. Do you
Like-
I think there's like a little.
No, I think I'm just gonna-
I think Sam's has like little heart boxes. Oh yeah, I remember just do those and then like buy bags. Are these Oreo balls?
Yeah,
Jordan
Jordan
brought
gave,
them?
Jordan gave.
Hey, you want?
Yeah.
Aren't they good?
Yes, they're
Can you
delicious.
pick for your graduation now?
Yeah, they're a great idea. I've been walking around since your period, so I must have walked on it by now. If it's out, I still,
I think it's been lost since fifth grade.
yeah, oh, I know it's been off my eyes since fifth grade.
Did you pick like over your desk or something?
No, I'm staying with you. I don't know.
Alright, well, good luck.
Thanks, pal.
Love you.
Thank you.
I'll see you. I'm home.
Hi.
Oh, what song is it? You know?
I think it's like this. Well, you can go on here.
Aaron Hallowell to the attendance office. Aaron Hallowell, please check the attendance window.
So you're signed up for my class and that's ready. Okay, sounds good. All right. Alrighty. Oh, I forgot to stop the recording. Oh, that sucks.